Okay, so where are we now? So we have 3 more classes, right? Not more than that. Today being, oh, what's going on? So the whole of next week and maybe 28th. So that's all we have. What happened? Just a moment, once more. Let's see. Oh, let's see. Okay, now what's going on? So can you see the white screen? No, probably not, right? Could you guys see the screen?
No.
No. Okay, yeah. Just a moment. I mean, it says that it's connected, but okay, one more time. Mhm. Hmm. Oh, finally. Good. Now you can see. Okay, so I think this is where we ended in the last class. We defined the length of a path. Okay, so the aim for today is to define what are called scalar line integrals and the vector line integrals. So let's just put the formula once more. Oops, sorry. No. No. Okay, I did something terrible. Anyway, let's rewrite the formula. So this was the length of a path just the integral from a to b of x prime of t dt. Okay, and let's see if it actually gives the length in some examples. Let's examples. First, the obvious one, you have the circle from 0 to 2 pi to r2. So this is defined by a cos t, comma a sin t. Okay. Now, how do we compute? Then the first step is x prime t. So the x prime is given by minus a sine t, and then this is a cosine of t. And the norm of x prime of t, so this is square root of minus a sine of t square plus a cosine of t square. So this is a square times sine square t plus cosine square of t. And all of you know this identity that this is equal to 1. So this is given by a. I mean, technically it's mod of a, but of course, a being the radius, you have that it's greater than 0. So this is a, okay? And hence the length in this case, the integral from, sorry, so 0 to 2 pi. So this is by definition, so 0 to 2 pi a dt and 2 pi a, as one should expect. So this is the circumference of the circle. So it indeed computes the length. Well, I mean, at least in this example, but just figuring out the definition, you can see that it computes the length. Next, the case of the helix. So xt being a cosine of t, a sine of t, and bt, sorry. Okay, so the z component is varying linearly in this case. Once again, you have a greater than 0, and the time varies between 0 and 2 pi, just to keep parity with the last example. Okay, so then what's x prime? I mean, these problems are of a similar type. So this is a sine of t, a cosine of t, and b. Okay? And hence the norm, so this is once again minus a sine of t square, a cosine of t square, plus b square. So in this case, what you have is a square plus this b square term, which comes from the z-axis. And hence the length, once again, this is 0 to 2 pi. Oops. So this is 2 pi times the square root of a square plus b square. So you have this b square term coming up because the helix also moves in the z-axis. That's the reason. Okay, so small observations. And all of this follows from the usual Riemann integration. So number 1, is the following that we call yeah, so we call this ST. So the integral from a to t of this norm, the arc length up to t. So it's a function of t. And from the fundamental theorem, we have S prime t equals the norm, or the derivative of the norm, rather. Okay, so that's the first one. And the second one is the following. Let's see. So if C is between A and B, then once again, from one property of Riemann integration that we did in the last class, so this integral is same as the integral from A to C, this norm. So it's the sum of the arc lengths. So the sum of the arc lengths from A to C and C to B. So this comes from one of the properties. Okay, so this is about the arc length. So what happens in arc length is the following, that you have, let's say, a path, let's say a string in R3 maybe, such that the density or the mass in each portion of the string doesn't vary. And then you compute the length of the arc using this formula. Now, what happens is that usually the strings may have variable density from one point to another. And still you want to compute the total mass of the string from point A to point B. And that's when you want to compute something known as the scalar line integrals. So the line integrals they are of two types. So number one is the scalar line integrals, simply because they're attached to the scalar fields, and the second type is the vector line integral. And the physical interpretation in this case is that it computes total mass, just to give an analogy, from variable density. And the vector line integral computes the work done. Oops. By a vector field. Okay. So the first one, the scalar line integral. Okay, now we do everything in R3, but just to remark that all of what we are going to do holds for general Euclidean space. So it holds for Rn, for n greater than or equal to 1, basically. So for any n. So let f from R3 to R be so we demand continuous so that we can integrate easily, basically. Continuous function, and xt from this interval AB to R3 be a path. Okay. Now, some observations, maybe A. So you can define this function f of xt. So can you tell me what this function signifies? I mean, in physical terms, and related to something we're talking about here. So scalar line integral computes total mass, let's say, from variable density. So this f on this path, let's say xt, this precisely computes this variable mass. Isn't it? I mean, f can be variable density. So for example, f can be the density function. So f at x of t, it computes the density at x of t. So this is the variable mass or variable density that one computes. So this is the analogy for variable density. at xt. Okay. Now we define two infinitesimal quantities. The first is ds. So ds, by definition, this is norm of x prime of t dt. So this is the scalar infinitesimal vector. Okay. And then we define the vector infinitesimal. So d vector s. So this is just the vector xt dt. So this is the vector infinitesimal. So this one we are going to use right now to define the scalar line integral, and this one is used for the vector line integrals. We will see how. So these observations, and then we have the definition. The scalar line integral of f along the path xt is given by, so let's use a notation. It's given by the following quantity. So integral from a to b. So f evaluated at xt, so this is the variable density, norm of x prime t dt. Okay, so it's not just this part, it's not just this part which computes the line integral, the length of the path, but you have this variable function too. So together, this product, so f of xt times norm of x prime t, it computes the infinitesimal mass at one point, and then you integrate from a to b to get the total mass. So that's the significance of a scalar line integral. Okay, so let's put this in some examples. First, some easy ones. So f from R3 to R. So xy plus z. So this is my scalar field or the scalar function. And my x of t is given by cosine of t. So the helix sine of t and t. Okay, so this is 0 less than or equal to t less than or equal to 2 pi. So we want to compute the scalar line integral along this helix for this function. Okay, so the scalar line integral is integral from a to b. So f of xt, the definition, then now what is f of xt? Can anybody tell me what's f of xt? From the definition, what is this? This quantity, t cos t plus sine t. Okay, is it? Once more. Exactly. Oh. Exactly. So yes, you did flip y and z. I mean, mistakes can happen. So as you were saying, so f of xt is cosine of t. So x times y plus z, cosine of t, sine of t, plus z is t. So this is my f of xt. So this integral a to b f of xt, what is this, x prime t dt. So this is a and b are 0 and 2 pi. So 0 to 2 pi, then this is cosine of t, sine of t plus t. And what is the norm of this x prime of t? We already computed. So this would be sine square t plus cos square t plus 1. Okay. And this is just root over 2. So this will come out. So this is root over 2. And now it's a matter of how good you are at computing Riemann integrals. Okay, and since I'm not really good at it, I cheated and I solved this before. Well, so this is a fairly simple integration. So this is half of sine of 2t plus t. So there's nothing much to do. So this is sine square t over 2 plus t square over 2, 0 to 2 pi. So this is 2 root 2 times pi square. Okay, so this is the total mass, or not total mass. If you can consider this as the density function, then yes, this is the total mass of this variable helix, you could say, the variable helix from the point 0 to 2 pi. Okay, so that's the physical significance once again. Now, as I was saying before, that solving integrals from a point A to another point B can be broken up. So you can take points in between, maybe 1 or 2 points, and the total integral is the sum of the integrals of those in between points, so to say. And let's see how we can use that. So sometimes, so this is the typical scenario, sometimes this could be a path, but only piecewise. So the term is called piecewise path. Okay, so let's write this example. So x of t is given by 2t comma t from 0 to 1, and t plus 1 and 5 minus 4t from 1 to 3. Now, if you look at the definition of a path, we considered the path to be continuously differentiable. Okay. Now, this function is of course continuous from 0 to 3. But there is an obvious problem with the differentiability at 1. So xt is not differentiable at t equals 1. Or a better way to write it is it's differentiable no, I don't want that. So how do I move? Anyway, so xt is differentiable everywhere except at t equals 1. Okay, so this is not really a path in the sense that we don't have continuously differentiable. So what is the picture of this particular path? So you start from 0, then you reach this point y equals 1, which is the point of non-differentiability. In the lecture note, there is a printing mistake. So I wrote point of discontinuity, not that, it's point of non-differentiability. So this is the point where xt is not differentiable. And then once again from here, it continues. So this should be a straight line. So 0 to, so this is 0, 0. Let's see. And this is 2, 1. And from here, it continues up to 2, 3, up to this point, which is 4, comma, so what is 5 minus 14? T is 3, so 12 minus 7. Okay, so this is how it looks like. Okay, so what we do is to consider xt as x1t plus x2t, where x1t is defined by 2t comma t between 0 less than or equal to t less than or equal to 1, and this is defined by the other component. So this is 5 minus 4t. Oh, sorry, not, it's the other way around. So this is t plus 1 comma 5 minus 4t between 1 and 3. Okay, and given any function, so given any scalar field, continuous scalar field f, this total integral f of xt x prime t dt, so this would be the sum over x1 and x2. Okay, so this is the whole idea. So given any continuous scalar field, we break this integral up in two parts. And this is valid from the property, one of the properties of Riemann integration that I mentioned in the last class. Okay, so let's take one particular example. So let's say f of xy. Oh, this is from R2, right? Not R3. R2. So let's take f of xy equals y minus x. Okay, so this is my scalar field. And then let's write out what the function evaluated at xt looks like for these two divisions. Okay, so what it would be between 0 and 1. So what is f of xt? So there are two divisions between 0 and 1 and 1 and 3. So what would be f of xt between 0 and 1? It's exactly t minus 2t which is minus t, of course. And the other one is 5 minus 4t minus t plus 1. So this is 4 minus 5t. Okay, so these are my f of xt. Now, the next step is to integrate from 0 to 3. So f of xt x prime t dt. So this is integration from 0 to 1 f of xt. Since I call this x1 and x2, well, let's continue with the notations of the problem. Dt plus from 1 to 3 oops. Okay, so these are my two integrals. Now one has to take care of this x prime t also. So x prime t, so this also has two parts. So this is 2 comma 1 in this interval, right? And 1 comma minus 4 in between this interval, right? Because for obvious reasons. So we have this paths. So you take the derivative. So it is 2 comma 1. And here it's 1 comma minus 4. So these are the two derivatives, and they are constants. So we have all the ingredients. So finally, we compute integration 0 to 3 f of xt x prime t. So this, now let's put in the values. So 0 to 1. So f of xt in 0 to 1, between 0 and 1, it's minus t. So it's minus t. And this is my x prime t. So it should be 2 square plus 1 dt. And between 1 and 3, it's 4 minus 5t square root of 1 plus minus 4 square dt. So these are, I mean, individually the integrals are fairly simple. So let's see what we have. So the first one is minus square root of 5 t square over 2 0 to 1 plus the next one. This is square root of 17 integration from 1 to 3. Well, let's do this completely. So this is 4t minus 5 over 2 t square from 1 to 3, and you don't need to get to the final answer, but anyway, so this is the answer, minus 5 over 2 root 5 over 2 minus 12 root 17. So this is a typical example of how you can use this breaking up an integral into parts. And there could be more points where the function is, where the path is not differentiable. So for example, a path might be something like this. So then you have 1, 2, 3, 4, 5 points. So you have to divide it into 1, 2, 3, 4, sorry. So 1, 2, 3, 4, 5, and 6 divisions. Well, but you don't have to bother about so many divisions. Typically, I would give just 1 or 2 points where the path is not differentiable. That's it. So any questions about it? It's clear, absolutely. I mean, if you have seen these things before, then it's not that hard. I mean, just following the definition and knowing some properties about Riemann integration, that's it. Okay, so seems like everybody understood what's going on. So we finished this third lecture note. So we finished VC3. And now we are moving to VC4. So today I uploaded 2 lecture notes. Let's see which ones. So now I will begin VC4. So VC4 and VC5, these are the 2 I uploaded today, just before the lecture. So I'll begin VC4. And of course, after scalar line integrals comes the vector line integral. So okay, and as I have mentioned, they compute the work done. Work done in moving a particle from point A to point B. And once again, we restrict in 3-dimensional space. So F is a vector field defined from a subset of R3 to itself. So this is the setup. And xt is a path. Okay. Now we define the vector line integral as follows. So this would be our notation. So the integral xt, f this d as vector, this by definition is given by integral a to b. So you take the dot product between f evaluated at xt with x prime of t, and then take this infinitesimal dt and integrate from a to b. So what does, first question, or let's say one question, the main question, what does this quantity computes? Or in general, what does this whole thing computes? So F is a vector field. So F applies this, let's say, the force on a particle moving in this path xt. Exactly. So this is the work. So this is the infinitesimal work, exactly. And if we integrate from A to B, we get the total work done. So that's, so in this case, the vector for vector line integrals, the analogy is very precise. So the vector line integral computes the work done by the vector field in moving a particle from A to B. So that's the physical interpretation. Okay, one moment. So since we have introduced this notation, let's introduce a notation for the scalar line integral too. Okay, so this was the definition. So let's use the following notation. So f of ds xt. Okay, so once the definition is clear, then we can do some simple examples. In this first case, a very simple, so this is called the identity vector field. Okay, and xt is given by t 3t square 2t cube. I mean, this example is just to see how this definition works. There's nothing more to it. And the t varies between 0 and 1. Okay? So x prime of t is given by 1, 6t, and 6t square. Okay? And f of xt is given by t 3t square. So it's the identity, so it will remain exactly the same. So this is f of xt. Then you need to take the dot product f of xt dot x prime t. So this is t 3t square 2t cube dot 1 6t 6t square. So this is given by t plus 18t cube plus 12t to the 5. Okay, so this is the dot product, and that's it. I mean, then you can compute the integral 0 to 1 t plus 18t cube plus 12t to the 5 dt. And I'll just give you the final answer since the integral is fairly simple. They're polynomials, so this is the final answer. Now, vector line integral. So this is one way to write out the vector line integrals, but another way which you see quite often is the following. So now f being a function from R3 to R itself, it has three components, f1, f2, and f3, right? And this xt being a path from AB to, from this closed interval AB to R3. So this also has three components, let's say. So xt is, so I'm differing the notation from the note a little bit. Well, right, so the path also has three components, and each x1, x2, x3, they're simply functions from the closed interval AB to R. So each xit is a function from continuously differentiable function from AB to R. Now, what do? You take f of xt dot x prime of t. Okay. So what is, in terms of this writing, so this is f1 of xt, f2 of xt, f3 of xt. Okay. And x prime of t, this is x1 prime of t, x2 prime of t, x3 prime of t. So finally, this f of xt dot x prime of t, in the shorthand, this can be written in the following way. So this is f1 times x1 prime t plus f2 times x2 prime of t plus f3 times x3 prime of t. Okay, so this vector line integral also has the following notation. So from time to time, you'll also see this notation. So this is f1 x1 prime Just a moment. Yeah, x1 prime Oh, a little bit more. Okay, let's continue. So x1 prime t plus f2 x2 prime t plus f3 x3 prime t dt. Okay. Now this is, if you bring the dt's inside, so this is f1 x1 prime t dt plus f2 x2 prime t dt plus f3 x3 prime t dt. So this is f1 d of x1 t plus f2 d of x2 t d of x3 t. Okay. And if you just rename x1, so we just rename x1t equals, let's say, capital X, x2t, capital Y, and x3t, capital Z, then this integral. So it's just a matter of notation. So f1 dx plus f2 dy plus f3 dz. Okay, so this is another expression basically, which can be derived from the usual one. Okay, so vector line integrals can also appear in this particular form. So let's see this particular example. Okay, so compute t So this is in this particular shape. Okay. Where, so I have to give you the path. So there are two cases. Number one is xt is fairly simple. So this is t square t cube, and 0 less than or equal to t less than or equal to 1. And number two, I will have to draw a picture. So now we are in VC4. So if you go to VC4, we are now at the end of page 3. So we have this 3-dimensional cube. So we have the cube in the following way. So we have L1, then L2, and then L3. Okay. And let me give you the point. So this is 1, 1, 0. This is 1, 1, 1. And so this is 0, 1, 1. So these are the 3 points. So in the second case, xt is L1 union L2 union L3. So the union of these 3 parts. Now you can write down a little bit more. So L1 is the following. So here x and y are the same. So you are basically going along the diagonal here. So x and y are the same, and the z coordinate is 0. Okay. On L2, you have that x and y, they are same, but they're constant. So they're 1, and z varies between 0 and 1. And on L3, you have y and z, they're constants, and x varies between 0 and 1. Okay, so first of all, is the path clear to everybody how it looks like for number 2? So I haven't given a parameterization of the path, but have drawn the picture and sort of described the path, how it looks like. If you want, you can parameterize on each L1, L2, and L3, but it's really not needed here. Okay, so we are going to compute the vector line integrals on these two paths, 1 and 2. So can anybody tell me what is the vector field hidden in this problem? So what is the vector field? Any idea? Look at this expression and then try to compare. So what is y plus z? No idea. So y plus z, so what does it compare to? So this is the first component of the vector field. Similarly, x plus z is the second component, and x plus y is the third component. So our vector field hidden is y plus z, comma, x plus z, and x plus y. So this is the vector field. But we don't really need the vector field here. I mean, we know the vector field, but we really need to compute this. Okay, the first one is fairly simple. It's a path t square tq from the interval 0 to 1. So for 1, there's nothing much to do. So for 1, the integral is given by 0 to 1. Now you substitute, so you have y plus z dx. Okay. Now substitute this components for y. So y is t square and z is t cube. So this is t square plus t cube dt, of course, plus t plus t cube, since the second component is x plus z. So t plus t cube. Once again, now here you have to be careful. Here you have t square, right? So you are really computing everything on xt. So then you have to compute d of t square, which is 2 dt. So this is d of t square, okay? Then finally, x plus y. So this is t plus t square. Once again, you have to compute d of t cube because you are computing everything on this path, okay? So finally, we have 0 to 1. So this is t square plus t cube dt. So this is 2 times dt. So 2 times 0 to 1 t plus t cube dt. and this is 3 times dt. So this is 0 to 1. Oh, sorry. No. Sorry, my bad. Sorry, so this is 2t. I need some coffee. So this is 2t dt, and this is 3t squared dt, exactly. So then this is, let's see. So there should be a t, so this is t square plus t to the 4. And the last one would be t cube plus t to the 4 dt. Could you explain why it is the second and the third derivative for the second and the third terms? So why I take dt square and dt cube? Because as I said, that we are doing everything on this path. So remember, if you check this formula, so what are we doing? So f1 times d of x1t, where this x1, x2, x3, these were the components of this path, right? So this is the point. So we have f1 d of x1t, f2 d of x2t, f3 d of x3t. So the x1, x2, and x3 in the first example is t. So x1t is t, x2t is t squared, x3t is t cubed. Okay. So hence, when we compute the integral, so this is t squared plus t cubed. So y plus z. So y is t squared and z is t cubed. So t squared plus t cubed. And it's dt simply because on the first component it's t. Then on the second component, it's x plus z times dy, and x plus z is t plus t cubed. So that's why it's t plus t cubed. But now remember that it's d of x2t. So x2t in this case is t squared. So that's why this is d of t squared, and similarly the last one. Okay, and so this is clear. So this was the question. Or was it something else? Okay, good. So hopefully I made things clear. It was that, but you still do not understand. The point is that, okay, so check the definition, the basic definition. So what is this integral? So f1 d of x1t, f2 d of x2t. So if you want to be more explicit, this is x1 xt rather. Sorry. So it's not d of anything, it's d of x1t, d of x2t. So you take the derivative of each component, right? So remember what x1, x2, and x3 are. So x1, x2, and x3 are the components of the path. Okay, so in our case, this is the path t, t squared, t cube. So t is our x1t, t square is x2t, and this is my x3t. Okay, so now if you follow the definition, so you have to take d of x1t, so it's just d of t, d of x2t, so it should be d of t square, and then d of x3t, which is d of t cube from this definition. Okay, so that's the reason why we take d of t square and d of t cube. So did I confuse you more, or is it clearer? So follow the definition. That's all I can say for the moment. And it should be clear why you need to take d of t square and d of t cube. Okay, and then it's just computing the integral, which shouldn't be that hard. I mean, the final answer. So this is the final answer, which is 3. Okay, so this was fairly simple since you were given the path. Now, for number 2. So this is slightly tricky. Let's do this slowly. So we need to compute this integral on this path, L1 union L2 union L3. And of course, we can do the following. We can compute, oh, is it the derivative? Yeah, it's the derivative of t square and t cube. So that's why it's 2t dt and 3t square dt. Yes. Yeah, it's the derivative of t square. No, not the second or third derivative. No, no, no. Yeah. Okay, so for number 2, what we can do is to compute this integral on each of these lines. So L1, L2, and L3. So on L1, we have, let's see if we can do this. Ah, come on. It's fine. At least this one. Come on. No. I'm messing up with, so this is L1 once again. Sorry about that. So this is x equals y. Okay, let's try once again. What exactly do I want? Okay. Yay, good. So this is the first line. Okay. Now here, so what's going on in this line? So we have that dz equals 0, of course, because z is 0. And dx equals dy, simply because x and y are equal. Okay. Now, if you integrate on L1 this function, so this was what we want to integrate, y plus z dx plus x plus z dy plus x plus y dz. Right? Now, dz is 0 on L1. And we are left with dx and dy. Now, since z is 0 and dx and dy are same, this can be written as L1 y plus x dx. Okay. Can everybody see what's going on here? So just on the first line, L1. And once more, since x and y are same, this is L1, sorry. This is same as integral on L1 2x dx. Okay, since x and y are same. And what is L1? L1 is basically the line, straight line, which varies from 0 to 1. So the x coordinate varies from 0 to 1, and so does the y coordinate. But we are only concerned with the x coordinate. So this is the integral from 0 to 1, 2x dx. So this is 1. Okay, so this is the integral on the first line. Okay. Now L2. So what was L2? So L2 was x equals y equals 1, and z varies between 0 and 1. So z is the variable in this case. And so here dx equals dy equals 0, because x and y are constants and z is the variable. So then on L2, if you, let's see, okay, copy. Let's try to, okay. Oops. Still have dz. Now on L2, let's like this. So then this is, so the dx and dy's being 0, this part goes away. And we're only left with the dz part. And now x and y are same, they're equal to 1. So it's simply 2 times dz. Okay, and then the z coordinate, it varies between 0 and 1. Okay, so this is the integral from 0 to 1 dz. So this is simply 2. So that's the value on L2. And finally on L3. So L3 is given by the last one. So this is y and z are constants. And 0 less than or equal to x less than or equal to 1. Now you have to remember the picture. Okay, so if you see the picture here on L3, the particle actually moves from position 1, 1, 1 to 0, 1, 1. So the x coordinate actually varies from 1 to 0, not the other way around. So you have to keep that in mind while doing the integral. So this is L3. So of course now dy and dz are zeros. Okay, and then the integral, the total integral, L3 of y plus z and so similarly this 2 goes away. So these are zeros. We are only left with the first component. So this is dx and y and z are 1, just like the computation on L2. So this is L3 2 times dx. But now here comes the point. So the thing is that x varies between 1 and 0. So this integral should be from 1 to 0, 2 times dx. Okay, and again from the property of Riemann integration, this is equal to minus integral from 0 to 1, 2 times dx. So this is minus 2. So there is a change of sign. I mean, this negative sign indicates that the particle moves from the position 1, 1, 1 to 0, 1, 1. Okay. So finally, the total integral, so this is L1 plus L2 plus L3. So this is given by, so what are the values? 1, 1 plus 2 minus 2. So this is 1. Okay, so this is the final answer. So sometimes paths can be given a little bit more geometrically in this way. And you have to figure out how. So always imagine a particle moving from path A, position A to position B, and you have to keep in mind how the particle moves. So if the parametric equation of the path is given, then it's fine. You are just given an easy integral, so you just need to do the dot products, etc. But sometimes paths can be a little bit more complicated like this. I mean, individually on L1, L2, and L3, they're simple, but then you have to keep track of what's going on. Okay, so this is the point where we stop today. So any questions about this last computation? It made sense, good, okay. Yeah, I'm happy that it made sense. Yeah, I mean, try to always make a physical sense of what's this integral or this vector line integrals compute. I mean, of course, vector line integrals computes work. So how the work is computed, that is also another question. And that is also determined by this sort of integrals. So when you break up the integrals, it gives you more insight, let's say, as to how the work is being done. Okay, anything else? If you have the lecture notes, it's pretty clearly written, so you can always refer to the lecture notes. And nowadays, I'm not deviating too much from the lecture notes. In an actual class, I can do that, but it's better to stick exactly to what's there in the notes. Anyway, so if there are no more questions, let's end here. So in the next 3 classes, we have just 3 more left. We will try to cover as much as we can. The initial plan was to go up to Green's theorem, but let's see. I mean, the next topic would be double integral and then computing some double integrals. So I don't know if we can reach Green's theorem or not, but we will see. Okay, so if there are no more questions, then have a nice weekend. Enjoy as much as you can. So, and if you want to stay on, I'll be back at 4. If you have nothing else to do, you can listen to the same lecture twice. Anyway, bye-bye. See you next week. Bye. Yeah, you too.